Uh, Good afternoon, everyone, for joining us for the afternoon session for this particular presentation. And Mr. Nilutpal, are you there? Can you hear me?
Yeah, I can hear you.
Okay, okay. So I welcome Mr. Nilutpal Choudhury, technical consultant from Embesys Technologies. Nilutpal completed his BTech in Electronics and Instrumentation Engineering in 2013 from National Institute of Technology, Silchar, and then did his MS in Communication Engineering in 2017 from Technical University, Munich. His specialization includes RF test and measurement, adaptive and array signal processing, antenna and RF front-end design, radar systems, MIMO systems, direction of arrival systems, and software-defined radio haptic technology. I am sure his talk on 5G prototyping massive MIMO and millimeter wave systems will be a great addition to our learning. Over to you, Nilutpal.
Thank you very much. A very good afternoon to the esteemed faculty members and the guests. It gives me immense pleasure to be a part of this consortium. So my agenda would be to actually bring more light in terms of the practical implementations of 5G, 4G networks. And at the same time, I'll be showing you some live demos that I have developed over the past few years. The idea would be to give a practical how it is kind of practically implemented in the hardwares. So the agenda would be kind of sorted out in the presentation in terms of like the massive MIMO systems, the millimeter wave systems, and some physical hardware demos. For that matter, actually, I have set up a system in my office wherein I have the setup ready. So I'll be showing you some demos on the National Instruments USRP 2920, and I will also show you certain IoT based applications that we have developed for the metering industry. So the entire presentation would be kind of concentrated in explaining the theoretical concepts on 5G. That's basically on massive MIMO and millimeter wave, the challenges being faced, where the industry is heading towards, and the other part would be on IoT and how we are trying to bring in and leverage the 5G networks for our IoT applications. So having said that, I'll just switch this off and I'll bring in the video again. So just to give a brief about the applications that I have been working on. So I have been working on some FPGA-based IP development for the communication technology. One of the applications that I have developed recently is a channelizer application. This channelizer application is for channelizing a bigger band or a broadband application into smaller subbands for us to process the subbands of the users. There is also a project that I implemented on open air interface using the ETS Research USRPs, wherein ETS Research software defined radio, wherein I have utilized the open air interface provided for 5G and 4G base stations to actually have a testing environment in place to test commercially off-the-shelf open cell mobile stations. I've been also working on the IoT aspect of things. Also, there is a huge impetus now on LoRaWAN applications. So this is one of my device level plans that I have, and we are working on IoT device applications, wherein we are trying to have meter data, electricity meter, water meter, and gas meter data available wirelessly through an IoT network. I will also demonstrate to you some end-to-end CISO, OFDM, and MIMO-based packetizer applications that I have developed, which will be demonstrated to you as a part of the session. There is also some control algorithms that we have developed for mitigating the head and held loading effects on the cellular headsets. That's primarily because like the antenna is a part of the cellular handset, and touching the phone basically reduces the antenna's resonance, basically disturbs the resonance frequency of the antenna due to the capacitive loading of the body, and how we can use certain control algorithms to actually mitigate the effect. And I will also show you a demo on, and I will also talk because this is an area that I have been very interested in, that is for AI for communications, particularly because with the 5G coming in, with the promising data rate which is available, we are at a very we are at a juncture wherein AI will slowly and steadily infuse with the communication engineering domain, and I believe that having an expertise or an or a taste for AI in communications is something which is futuristic and would be beneficial both from the professional and the academic domain. Uh, so the ITR vision for 5G is kind of very high-fetched mainly. So if I need to broaden it out in three ways, it will be the immersive experience for the broadband users. So we bring in very high data rate, over the air data rate. It is expected to be 10 Gbps. That's partly because of the way we are trying to design our base stations and mobile stations or user equipments accordingly. So to say, the 4G network which is there is already providing a decent speed, but 5G comes up with certain ideas, certain standardization that will kind of enhance the peak data rate. The second in line where 5G focuses on is basically device to device or machine to machine communications, wherein we envision to bring in a lot of devices under a same network, such that one device can communicate with the other, and that too intelligently, such that we are able to make processing or decision making much more faster between devices to devices or machine to machine. The second one is the ultra reliability factor, which will be coming in because we are kind of looking forward for network systems which are less than 1 millisecond, which are having latency of less than 1 millisecond. So ultra reliability will also bring in another form of internet, which is called as a tactile internet, where affordable surgeries, over the network surgeries, control systems over the network control systems would be made much more feasible. With that respect in mind, there is one part which is focusing on the broadband communication, or like the mobile communication cellular technology, wherein we are trying to improve the data rate, that is over the air data rate that the users are currently experiencing. The other one is basically bringing a lot of billions of devices under one particular purview, and connecting them in a way that device to device communication, intelligent machine to machine communication is possible, and decision making is done without a central processor being involved. With the ultra reliability, we are focusing on low latency networks such that control systems over the network are possible. This is particularly very important in case of the healthcare technologies which are revealing today, wherein operations from, for example, a surgeon sitting in US can operate in India. That's particularly because the latencies we are bringing lower latencies, and hence operations across will be much more easier. This basically brings into the fact that we have kindly currently three to four divisions of research on 5G. One is the massive MIMO, as you all might be knowing, kind of bifurcating from the traditional MIMO systems mainly, wherein we are planning for 64 to 128 antennas on the base station, and hence the complexity to maintain or do the signal processing involved in that has also increased manifold. So the idea is to actually bring in certain elements or certain innovations in place that can actually reduce the complexity or allow us to handle the complexity which is not very evident in the, or which is not being utilized in the market offerings presently available today. In the millimeter wave spectrum, you might be knowing this already. There is a cutthroat competition among the mobile service providers. There are so many mobile providers now that are coming in globally, nationally. There is a cutthroat competition with respect to the spectrum allocation. So obviously, we want to go ahead and venture upon the unutilized or less utilized spectrum spaces, such that we can actually reduce the complexity, reduce the competitions among the service providers mainly. And hence the millimeter wave, which comes with its own set of challenges, of course, would be one of the and one of the research areas. Not only academics, but a lot of industries like Nokia, Verizon, AT&T are working towards bringing in the millimeter wave concept in place. Multi-rate radio access technologies is one of another aspects of it. Take, for example, you have 4G, you have 5G, you have Wi-Fi. Now the challenge is how to actually leverage from each of the existing technologies, in a coexistential manner mainly, wherein like they will be having a 5G, a 4G, and a Wi-Fi network, and how a user can leverage from all those three networks coexisting together. Wireless network, massive MIMO, millimeter wave, and multi-rate somewhere down the line falls within the physical, in the OSI model, falls within the physical and till the network layer of things. Wireless tech networks is mostly for CRAN, SDN densification of networks, mostly used for large scale deployments, such as smart cities, smart villages, wherein we would be having the concepts of femtocells, and we will be leveraging the massive MIMOs inside the femtocells to actually densify the network. This is particularly very important in terms of like the consumer technologies which are coming in, wherein we would be able to leverage on the network infrastructure which will be available with the 5G being established. So coming to massive MIMO, basically massive MIMO means that we are increasing the number of antennas for say. So according to the Shannon-Hartley theorem, which says that channel capacity is equal to the product of the bandwidth and the logarithmic of the SNR. The conventional MIMO says that if we need to increase the channel capacity, keeping the bandwidth the same, and if we need to increase the channel capacity, or so to say the data rate, we need to we either need to increase the bandwidth or the SNR mainly. But both of them being constrained to certain factors which we don't have much hold of, it is kind of imperative to actually come up with solutions that can actually increase the data rate, giving the constraint of the bandwidth and the SNR. So to say, the MIMO came into existence in around 1986 in a commercial way, wherein we adopted to MIMO, and it increased the channel capacity to a great extent. But whatsoever the massive, if you want to have an OTA rate of around 10 Gbps, it is very natural that we need to increase the number of antennas on both the base station as well as on the UV side. So the massive MIMO kind of promises to bring in the capacity to a massive multiplication increase of 10. The energy efficiency is expected to increase by 100%. There should be lower latency because we will be using certain directive beams, and at the same time on the networking side we would be using certain algorithms of routing and switching. We are planning, or we are envisioning that the latency will go low, more robust to interference, of course, because of the massive MIMO coming in, and high reliability. So with this in mind, this is the primary objectives of the massive MIMO systems mainly, wherein we are using antennas which are more in number than what is presently available on the 4G LTE networks, and with that we would be coming in with certain techniques, beamforming techniques like hybrid beamforming, which is a combination of both the analog beamforming and the digital beamforming, to actually cater to large number of users with high speed and high reliability and with low latency in the network mainly. For this massive MIMO, theoretically 10x capacity gain. Theoretically is the 10x capacity gain. With this, we have certain prototyping systems in place in the market today. The one which I have a hands-on experience on is on the National Instruments massive MIMO, wherein you have a setup which acts like a base station, and then there are certain software-defined radios that acts as your user equipment. With this in mind, the idea is to actually come up with certain ideas on or not only on the theoretical part of things, but also on the practical implementation of the massive MIMO. The practical implementation of a massive MIMO, as you might be already knowing, that we would be actually using an array of antennas, and based on the array of or based on the way we change the weights of the or the phase of the array of the antennas, we will mix the analog beamforming with the digital beamforming, and that's how we will be coming up with the hybrid beamforming technique. So the problem with the analog beamforming is that even though it uses only one chain, RF chain, but there needs to be phase shifters mainly. The phase shifters need to be there at every element of the antenna, and there need to be a very time precise algorithm in place, possibly an FPGA, for example, to change the phase of the antennas. Again, on the digital beamforming side, you need dedicated RF chains or baseband chains, mainly not RF chains, baseband chains for each of the elements of the antenna array, because of which it becomes a very on the power consumption side, it becomes very intensive. To to have the trade-offs for both of them, even though digital precoding or digital beamforming is easier to implement, and analog beamforming, which consumes less power but has a very heavy usage on the processing side. So in order to bring the two things together, there is a hybrid beamforming concept which is being currently proposed, which will be utilizing the digital beamformers, will be grouping we'll be grouping two things. We'll be grouping certain antennas together as one sub array. We'll be doing the digital precoding and then giving it to an analog beamformer and doing the phase shifting again. So in a nutshell, it will be a combination of a digital beamforming and an analog beamforming together. So the road to massive MIMO in 5G is basically distributed massive MIMOs. You require hybrid beamforming, high mobility applications. For example, we are also the future is to use 5G networks, in fact, for manless cars, for V2X communication, vehicle to anything communication. So it has to have the capability to mitigate high Doppler effects, high carrier frequency offsets. It has to have the mobility, it has to has that intelligence to actually estimate the channel at a very fast manner. So it has to be energy efficient, because it finally 5G, not only in the base station side, you can of course go ahead and put as much power as you want, but you basically cannot do the same in terms of the mobile applications or the mobile users mainly. So for that reason, we have to be power optimized as well when we're using it, and there need to be a massive change on the network infrastructure what we have currently. So these are some of the open research areas that we have seen that is coming up mainly in some time from now, wherein like we're concentrating on distributed massive MIMOs, wherein we will be having massive MIMO base stations spread across the geography, and we'll be finding out ways or network topologies in which you can bind them together. High mobility applications, as I already told you, is basically for V2X communications. Antenna patterns is becoming very important, even though most of the time when I look into when I do wireless signal processing, the RF part does not come into picture, or the carrier frequency part does not come much into picture, and you work more on the IQ side of things or the baseband side of things. But what is important here is that the antenna patterns or the antenna engineers need to actually design very directive antennas, because we'll be using the directivity of these antennas to bring in or to electronically steer the beam. Hybrid beamforming, as I already told you, improvement in CSI feedback is required, because everything has to be fast. So the feedback either from the receiver or utilizing the channel reciprocity concept between the transmitter and receiver, the CSI feedback has to be much more faster. It has to be much more accurate to gauge the channel. More importantly, with the millimeter wave coming in, the currently existing channel models which are there, that would be kind of eradicated out, and we will be coming up with the millimeter wave channel models, for which the CSIs, calculating the CSIs will be another challenge. MAC layer control for packet scheduling is one of the challenges, even though I'm not that well versed with the data link layer and the network layer because I work more on the physical layer side. But MAC layer control network protocols would come into picture, and spectrum sharing is something which is of great importance. I will in a short while from now I will kind of also bring some light to the spectrum sharing which can be done on the 5G and the 4G networks using AI for communications. That is one of the areas that is coming into picture, and I am also investing a lot of time on that. Uh, these are some of the universities and industries which have already started prototyping 5G systems. Lund University, KU Leuven, University of Bristol, Lund University. I have personally visited. They have a massive MIMO system set up there. Facebook, Intel, Samsung, to name a few, and also telecom companies like AT&T, Verizon, uh, Nokia Bell Labs, Samsung, all of them are actually on the verge of coming up with 5G solutions, both on the base station side as well as on the mobile side. Even though the challenges are more on the mobile side because you have to miniaturize it, you have to make the power consumptions as low as possible, and also come up with certain solutions that can adapt to the evolving 5G technology. These are some of the massive MIMO successes. Like Facebook has announced this Aries testbed, which can give them a 71 bits per second per hertz. Mainly, they're using around 96 antennas, and they have a lab testing which has been done on 24 users. This is way back in April 2016, and this is from the Bristol University, wherein you can see that these are the massive MIMO setups mainly which are existing, and these are the mobile equipment users, each connected with a laptop. So basically what we are doing is we are emulating the base station using this stack of software defined radios with each antennas, and then we are using a user equipment for which is acting like a mobile station mainly. So the prototyping is done in a way that allows you to have a base station in place wherein you are translating the 5G standards into the base station, and at the same time there are user equipments in place that is actually putting in the technologies required on the mobile station, and you're validating the wireless link accordingly. This is one of the Intel massive MIMO systems mainly, wherein you can see that in the uplink we are doing the channel estimation, the MIMO detection, and then on the downlink side we are doing the pre-coding. We are doing the pre-coding for beamforming mainly. So I will explain all of this in a short while from now in a more better way. So this is one thing that Intel has done. On the hardware side, I would like to bring in the National Instruments platform in place because that's where I have worked on and I have experience on mainly on the practical side of things. So basically, to be more general, it uses the software-defined radios as the radio heads. So you can consider that the baseband chains or the RF chains that are existing is provided by the USRPs mainly, or the software-defined radio. There needs to be a controller mainly in place, so the PXI basically works as the controller. In order to have a timing control across each of them, we need a timing control module mainly. So that is provided by this PXI 6674 and CDA 2990. Then there is the baseband. So since massive MIMO is very intensive when it comes to the baseband processing, even though the USRPs or the software defined radios has an FPGA by itself, you cannot basically rely completely on the USRP radios FPGA because the FPGA is resource limited, as you might be already knowing that the FPGA has a limited number of resources, because of which relying only on the FPGAs on the USRP is kind of not something that you would like to do, because of which an offloading is done on some baseband processing cards. These baseband processing cards are FPGAs and DSPs, wherein you offload certain FPGA based processing in here. And then of course there is then there is a CDA2990 which generates external signals, and generating external signals you would be able to synchronize the transmitters and the receivers, because in a massive MIMO or in a conventional MIMO the need of the hour is to synchronize the transmitters and the receivers. That is particularly because if you look into it, if I need to go into the granularity of things, if you have, like for example, a 2x2 MIMO setup, In that case, what happens is in a 2x2 MIMO setup, two transmitters and two receivers are there. So one transmitter might have an independent phase noise and the carrier frequency offsets, and the other might have an independent carrier frequency offset and the phase noise. So the idea is to actually share the reference signals between two transmitters, the reference signals that are used for generating the local oscillator and for generating the sampling clock mainly. So what we do is we allow both the transmitters to use the same or share the same local oscillator in a very general terms, share the same local oscillator and to share the same PPS clock for the sampling clock or the sampling clock mainly. So this is how normally a setup, any kind of setup would look like. There would be, you can cluster the radio heads. So normally we cluster in the form of 2 to the power n. So you have basically the radio heads, which is your actual devices that are transmitting it in the carrier frequency that you want. Also, you need a PCI switch box or any kind of a switch box to basically switch between the USRPs if required. Then there are the CDA2990s. The CDA2990s are basically used for synchronizing these transmitters and the receivers together. So this 8 USRPs that you see, they are basically synchronized using the CDA2990. And then there is a master octaclock or a master timing module that is used for synchronizing the slave timing devices parallelly mainly. So all of this slaves are synchronized with one another, which in turn synchronizes the clusters of the radio heads mainly. So this is how a practical implementation is being done. Actually, my aim was to show you an actual setup of a base station, a 5G base station, but because of this COVID situation, I was not able to manage a complete base station because it's a pretty huge base station that I could have showed you, but that's kind of unavailable right now. So I would try to show you more in terms of like the USRPs that I will be demonstrating with. And then there will be a host computer wherein you will be running your UI or giving some user commands with it mainly. So a base station, typically when you are prototyping a massive MIMO base station, you will have, so this will make it more clear, you will have USRPs, which are the radio heads. Then you have the PCI switch boxes for connecting the USRPs with the host computer. Then you would have CDA2990s or like any kind of an octaclock setup or any kind of a timing synchronizer setup mainly. And this timing synchronizer setup, individually each of the timing synchronization setups will be timed with another timing setup to synchronize them together. So in turn you're synchronizing all the 64 radio heads together mainly, and that is the base part of it. And then you have the PXI chassis wherein you would be controlling, you would be all the baseband data that you're acquiring from the USRPs or from the SDR, software defined radios, would be actually going to this PXI system, wherein you would be using the baseband processors, as I already showed you, the baseband processors for actually doing the baseband processing. So this is the overall architecture that is normally followed in terms of like in terms of setting up a massive MIMO system. And this is in general, whether it be from National Instruments or it from another XYZ company, this is the kind of a hardware stack that follows, wherein you have the radio heads, which will be acting like your radio, wherein you have the SDRs, which will be acting like the radio heads on the base station. Then you have some synchronization modules, timing and synchronization modules to synchronize the individual clusters together. Then you have the master synchronizer, timing synchronizer, which will synchronize all this individual timing synchronization blocks together. And then the data that you are receiving are actually going to a host or a ruggedized host system, wherein you will have different baseband cards mainly, or FPGA baseband cards to be very specific, where you'll be implementing your algorithms mainly, like for example the hybrid algorithm, hybrid beamforming algorithm, or a simple digital pre-coding algorithm. Whatever it is, you'll be actually kind of because your bandwidth is quite high, because your streaming rates are very high, you would not be able to implement it on a general purpose operating system like a Windows system mainly. So you need to have dedicated FPGA resources for actually implementing that. So single antenna mobile station is where like we'll be using a single SDR, a simple SDR actually, which will be connected to the host computer, and this will be acting like the user, the user equipment mainly. So this would be your base station who will be giving you the downlink, and this one will be receiving the downlink, and then again on the other hand, this one will be sorry this one will be giving the uplink, and this one would be receiving it mainly. So this is how the practical setup looks like mainly in the massive MIMO setup, wherein you have two single antenna mobile station, and each Rio has two independent RF channels mainly, or like the SDRs have two independent RF channels. So I will come to this a little later. So this is how the standard MIMO configuration looks like. So if you want, suppose 8, basically each SDRs normally, which is available in the market, most of the SDRs are having two RF channels. So you would be placing, so if you want an 8 system, 8 cross 8, in that case, you would have 4 of the SDRs, wherein individually one antenna is connected to one RF channel, and hence you have a 2 cross 4, 2 into 4, hence 8 cross 8 is possible. So you can see that this stack will keep on increasing as we increase the number of antennas. So for a 128 you would require a 64, so you would require 64 SDRs currently, and this will be the user equipments mainly. Yeah, so massive MIMO base station system, the diagram looks something like this mainly, even though you can do a lot of customization by yourself, but this is how it looks like. As I told you, the major baseband part, if you can see my mouse cursor, the major baseband part is being done on the FPGA modules or on the baseband processors mainly. The downlink part, FPGA part, is also done using this. The host or your computer, let us consider it like a general purpose operating system computer. So your computer basically is used for receiving a chunk of data and displaying it to the user, configuring the system, channel, looking into how the channel looks like, how the channel response looks like, and the radio heads, which are your SDRs mainly, would be used for your so what we are doing currently is that the SDRs which are there on the FPGA of the SDRs, we are actually doing the OFDM implementation, which I'm going to show you. We are doing the OFDM implementation, and then there is the RF front end. So RF front end is very straightforward. You can tune the carrier frequency, you can tune the sampling rate that you want, you can tune the gain of the power amplifier and the low noise amplifier that you want. So there are certain tunable RF parameters that you can set using the RF front end, and then you can do the OFDM baseband processing on the USRP itself. And other than that, whatever other the baseband processing requirements are, such as like the channel estimation, the MIMO decoding, the QAM demodulation, all of them can be done on the baseband processors, which are outside the radio heads mainly. On the software side, so this is how a basic prototyping system looks like mainly. There are a few other companies who also provide, like Newtek provides a 5G prototyping system as well. But I prefer working with, because of my previous experience at National Instruments, I prefer working on the NI MIMO prototyping system because of my previous expertise that I have. So this is the overall base station that looks like, and this is what I intend to actually show it to you in physically as well. So this is the baseband part of things, wherein all your FPGA modules, uplink and downlink modules, are being implemented here, and the OFDM implementation, or the OFDM baseband side, like making the OFDM chain per se, is being done in the radio heads FPGA. And the antennas, as you can see, is connected with the USRPs mainly, or the SDRs, software defined radios, which will allow you to actually transmit and receive data mainly. So this is the packet structure. So you might be already knowing that the LTE OFDM has around 10 milliseconds as the packet time mainly. So we divide it into separate subframes, and we use this to utilize this frame for sending certain data on a massive MIMO setup, and checking out whether the mobile stations, or when I say mobile stations, just consider it to be the user equipments. I might be intermittently using the two words together. So for the mobile stations to actually validate whatever data is being sent by the base station, are we receiving it or not? Either we are receiving what is the downlink transmission rate, what is the uplink transmission rate. So you can basically, and how the packets needs to be timed. All of this has been all of this in the terms of the frame structure can be well implemented mainly. So I need to talk about, I think when it comes to massive MIMO channel, the channel reciprocity becomes very important mainly. So we follow the uplink and downlink channel responses. We consider it to be reciprocal, and hence, for example, if you want to find the CSI from the transmitters to the receiver, or from the receiver to the transmitter, you can consider the channel to be reciprocal, and hence if you found out for one, you can find out the reciprocal or the inverse index, or the inverse matrix for the same mainly. So this is when your transmit, you also require something called as the RF calibration, or the channel reciprocity calibration. This is something that we do before we send the data, or before we send the data from the base station to the mobile station. That is basically because if you look into it, there are so many antennas involved mainly, and that RF calibration becomes important because there is mutual coupling among the antennas. There might be certain leakages on the RF chains. So because of all these reasons, we need to actually bring in an RF calibration stage right at the beginning, such that when we are sending, or when we are establishing the uplink or the downlink, we are kind of sure that the calibration is done right both on the base station. This is an advanced reciprocity calibration setup mainly. I'll not dwell much into that. I'll come into this millimeter wave problems mainly. So one of the increased problems that you might be, so this is part of what I wanted to show on the massive MIMO side. On the millimeter wave, the difficulties or the challenges that we're currently facing is the path loss, right? So you might be already aware that we are going for higher frequency ranges. We are going from 30 gigahertz, and in fact the plan is to go to 300 gigahertz. So one of the biggest challenges which I think is in place is that when you go more and more, from my experience, what I feel is that when you go more and more towards higher frequencies, your electronics tend to become unstable, right? And that too, if you try to miniaturize the electronics, it becomes even more difficult to actually, it becomes more difficult for you to actually stabilize the electronics involved. Take for example, we come up with, for example, if you're using a 28 gigahertz, right, for communications, it will be very difficult to actually maintain the stability in the electronics. So first of all, more than the system level of things, I believe that there is a lot of work and a lot of research that needs to be done on the RF electronics part as well, because we are planning to use high frequency devices for it, and hence our oscillators, our local oscillators, particularly our numerically controlled oscillators, our baseband processors, has to be able, and with millimeter wave again, there is a high bandwidth requirement as well. So with all this in mind, it is very important that we come up with certain ideas and that can stabilize the electronics at the very beginning. When it comes to the wave propagation side also, the path loss becomes very evident. That's particularly because when we are increasing the frequency, the wavelength would obviously decrease, right? Because C is equal to lambda f, so it would decrease, the frequency is inverse in proportion to the wavelength, and hence the effective electrical aperture of the antennas would reduce to a great extent, and hence the power falling on the receive antennas would be much lower. So keeping a constant aperture is kind of a solution that we have come up with, but even then, like, there are a lot of challenges to it. So path loss is one of them, because your path loss would be in an exponential proportion with lambda square mainly, and the millimeter wave also, because millimeter wave will have lower wavelengths. So consider the 3 gigahertz spectrum, where the cellular networks are using that 3 gigahertz spectrum. Here, the another difficulty that will come into picture is that the the microwave waves, the microwaves in general used to get used to face diffractions, right? Because of which there is fading mainly. On the other hand, with the higher frequencies coming in, there will be complete blockages mainly. So how we will be able to come up with the data rates with the blockages in picture, taking for example the urban clutters or like the urban areas in place. That is another thing which is of prime importance mainly. And there is certain channel models which you might be already aware of, being from the academia. You might be aware of that has been developed, the certain channel models, because all the existing channel models which are currently being used, those are basically tested for lower frequencies, the sub gigahertz range mainly. But with the higher frequencies, with the higher frequencies coming in, there needs to be a complete revamping of the entire channel models, and that again poses as a big problem. Again, like currently the LT is using the multi-user OFDM MIMO mainly. So when we use an OFDM, we come up with a very intrinsic problem, which I believe that most of you have researched upon, and I believe that most of you might have already worked upon, is the PAPR ratio, right? Peak to average power ratio. So PAPR is something that OFDM comes intrinsically, even though there are certain solutions that has come up with it. There is clipping solution, there is submerging solution, there is certain hybrid solutions between clipping and submerging. So there are so many solutions that have come up with it. So, but like with the millimeter wave coming in, the push of the research community as well as from the industry as well has been towards some non-orthogonal or NOMA-based approach mainly. So NOMA is one of the waveforms that is currently being investigated. There is another GFDMA waveform that is currently being investigated, even though like nothing has been fixed per se, or nothing has been communicated per se as an official thing. But there are certain waveforms wherein we are trying to replace the OFDM. So there is a waveform research that has also erupted out of this millimeter wave research mainly, which you can consider to be a sub branch of this millimeter wave research mainly. Again, on the main difficulties are acquiring and tracking user devices with the coverage area of base stations using a narrow beam antenna. Again on the massive MIMO side, it's kind of contradictory mainly, because on the massive MIMO side we are planning to make small narrow beam antennas, and at the same time we require to have a coverage area with this millimeter wave for a large number of users maybe. So it's kind of paradoxical and kind of contradictory with one another. So that is a difficulty, and that is kind of a trade-off that we have to do with the millimeter wave coming into picture, and with a massive MIMO setup for sending and receiving this millimeter wave in place. We need to come with a trade-off that can actually solve this problem. Uh, Normally, I would say this is how the setup, the any kind of a millimeter wave setup looks like mainly on the practical scenario. There is most of the equipments, if you see today in this market today, although there are certain equipments that comes very expensive and are tagged for very high frequency high frequency operations, like for radars and all. But most of the prototyping systems that are existing in the market today, those are all in the range of 6 gigahertz. I'm not talking about the test and measurement equipments. I'm talking about the prototyping systems per se. So these are all mostly on the 6 gigahertz range. So many companies have come up with some super radio heads, wherein you would be having a custom radio which is built in for millimeter wave application. Companies like National Instruments, companies like Agilent and all have come up with certain radio heads on this. So the idea is that you will have an IF or an LO module mainly, and then after that, I will talk in terms of the transmitter first. So you will have the data, you will have the FPGA processing module, then you have the baseband transmitter mainly, then you have the IF. So you basically have a super heterodyne architecture. What I mean to say is you need to have a super heterodyne architecture in place, when you have the IF and the LO module, wherein your carrier frequency is first converted into intermediate frequency, and then it is converted to a very high frequency in the 20 gigahertz, 30 gigahertz, or even like 70 gigahertz range. Because a direct conversion or a zero intermediate frequency conversion directly from baseband to such a high frequency is kind of not possible, because if you try to do that, you might be already knowing that homodyne architectures follows through certain problems like local oscillatory image LO image mainly, which comes and which can be eradicated, of course, but basically there is an LO image problem which exists on the ZIF architectures or zero intermediate frequency architectures and the homodyne architectures, and there is also the architecture. Then there is also a problem of the bandwidth as well on the ZIF. So it has to be well managed, and for that reason, a super heterodyne architecture is the need of the hour for the millimeter wave, and hence companies who have come up with this have kind of made customized radio heads which can connect to this existing 6 gigahertz prototyping systems. You can connect it to them and you can generate higher frequencies out of it. So a millimeter wave definitely is going towards a trend of a super heterodyne architecture or when it comes to the transmitters and the receivers. This is one report that I was going yesterday actually, and I thought like I would share it with you. So a few of the test cases which has been done on the company side on the industrial side is one of them is AT&T fixed 5G wireless network. I was just going through a few of the practical implementations, so to say, that the companies have done. So they have already come up with a 5G NR mainly, and they were visioning to have the 2000 by 2018 and 2019 the millimeter wave cell phones, but it is kind of far-fetched at this point of time because there are a lot of things that needs to be put together and bring into existence to actually make a 5G cellular headset possible maybe. So there is the 5G trial service is kind of distributed through a number of Wi-Fi access points to serve around 5,000 customers. So basically, this is a test case that they did a couple of years ago, mainly, which I find interesting for you with you, and I thought of sharing with you mainly. It kind of did a test run. So it got a decent 1 Gbps download rate, which is good enough, which is promising, and then the latency was less than 10 milliseconds. More interestingly, Bell Labs have also come up with a lab setup, mainly where they have got 14 Gbps over the air, and with 500 users perhaps, and they have also received a latency of 1 millisecond. So the research has further increased. Verizon has also tried with certain 5G wireless networks. They have also deployed in certain networks, gave a test run. So till now, whatsoever we are able to come up to 1 Gbps, and with the 5G NR radio coming in, it is very highly likable that we would be able to achieve the OTA rate of 10 Gbps and above. 5G NR stack has already. This is a project that I'm currently working on as a consultant, wherein I'm trying to implement the 5G NR and the 5G NR as well as the 4G NR in a coexistential way in an SDR mainly. So this is a very interesting project because the opener interface community has already developed a stack which is on 5G NR mainly, and my work is basically to implement the stack into an actual hardware. So they have given the hardware, they have given the stack to you, and now it is on my part to actually understand the stack, understand the physical, the file layer, the PHY layer, the MAC layer, and then integrate it as a complete solution mainly. Uh, I would like to, since it's already past like my time, I would like to actually kind of bring into certain practical implementations into existence, and I would also like to suggest as in how I basically learned about the 5G and the 4G prototyping systems and what helped me out. Even like I'm going to show you certain reference frameworks which I have designed mainly for the academia and the industry to start working on the 4G and the 5G networks mainly. So this will be all practical implementation. So the setup looks something like this currently. So I'll be showing you one IoT demo as well, which is kind of a proprietary and patented technology that I have developed for the 5G for in terms of IoT for 5G mainly. And there are certain SDRs that I had in my office, which I would like to show you some demos with mainly. This is the setup. These setups are actually connected to my host computer mainly, and the IoT node is also connected to my host computer. There is a laptop parallelly connected to it. It is connected, the SDRs are connected using an Ethernet cable. The IoT node is connected using USB A to B cable. I will stop the camera because it takes up a lot of bandwidth otherwise. I'll keep it like this for you to see the green light. So first of all, I would like to also talk about a little on the AI for communication before I show you the demo. I have designed one algorithm in place using a ResNet model, wherein I will show you exactly how you can use an SDR network, and with the 5G bringing in a lot of impetus on artificial intelligence or signal processing. The idea is to show you a demo on how getting only the waveforms and the receiver not having any kind of an a priori information about the modulation schemes can use an AI model to classify the different signals. And this is, if you look into different aspects in which the academia outside India also working on. This is one of the aspect in which spectrum sharing or cognitive radio is evolving too in terms of 5G. So in 5G, when it comes to cognitive radio, there has been a lot of impetus that has been put on machine learning and artificial intelligence model, particularly because the statistical models, when in fact, like, I have practical experience on implementing FPGA statistical FPGA models into place, and I feel that the resource that the complexity in both in terms of time and both in terms of resources is quite high mainly. So if you can bring in an AI model in place which can actually replace the estimations and optimizations which has been previously done by traditional statistical methods, then the communication engineering community or the domain per se can actually improve to a great, can actually evolve into the next generation mainly. So here what I've done is there is this USRP, and I will be just connecting it with a TensorFlow at the back end. And then what I would be doing is, like, you would be receiving. So right now I have a transmitter in place. I have a transmitter in place where right now I'm generating an 8 PSK. So you would see that it is being predicted as a PSK8 mainly. Now I would be, so this is the USRP that is transmitting it mainly, and there is another USRP which is receiving it. Then I would change it to some other one. So let's suppose FSK mainly, or let's suppose PAM, and I just apply the changes. So it is a PAM signal which will be selected now, and I'm expecting that it should change to PAM. And basically the receiver receives the IQ samples. I'm not going into the details about the IQ architecture of the SDRs, considering that you already know about it. So what I basically do, or as an algorithm, is that I take the IQ samples, I generate several data sets out of it, I generate the IQ data, feed it on a ResNet model, a residual neural network model, which is basically a variant of the convolution neural network model. So normally you might be knowing this, that convolution neural networks are mostly used for image processing or image recognition per se. What we have done is we have tried to use it for signal classification. So right now with this current model in place, you can segregate up till, or classify up till 8 modulation schemes without the receiver knowing about it mainly. So if I just need to go more into the demo part of things, you can see that, suppose for example I need to generate the FM. So let me say that I want to generate an FM with 40K mainly, right? So, and I start apply the change. So this is the FM, and let's see whether it's able to get it or not mainly. So see, this is now this scheme, perhaps because of some reason, it may not be able to stabilize, the AI may not be able to stabilize at FM, and the predictions might be going from FM to certain other as well. So this is how the AI would be working at the back end, wherein it would be receiving the data. The AI has been already trained on several data sets. We have used around 50 GB of data for training the AI, and for the deployment purpose, we are randomly generating data. You might be, once I stop the demo, I will show you how we are kind of using the testing accuracy versus the SNR. The SNR, we are changing only the transmitted SNR for the time being, wherein we are changing the power amplifier gain, and hence we are able to change the the transmitted SNR mainly. So this is particularly an AI algorithm that we have developed on actual hardware. Not many companies in India working on this. So the next phase that we are trying out is basically translating this whole concept into an FPGA. So whatever models that we are making right now is running on the general purpose operating system. But what we will do is we will take this model out and put it on an FPGA such that you can carry on an SDR with you, and then the SDR would be able to tell you on field. So for example, this application is very much used as a signal classification application, is very much used in the defense domain. So what they will do is the people on the border area, the our soldiers on the border area can actually carry on a device which can actually predict the kind of modulation. It will also predict the symbol rate, and based on that you would be able to do blind demodulation mainly. So this is one of the ways in which we do it. And you can see this, there is a confusion matrix which tells about which schemes will get confused with the other. For example, when we were doing or developing this prototype, we were facing a lot of problems when it comes to QAM and QPSK, and that's very natural, right? Because QAM and QPSK almost looks the same. So there are certain other modulation schemes, and we are scaling this application up to 26 modulation schemes, almost like encompassing all the modulation schemes that is available. We have checked it out with the SNRs. We have checked it out with the SNRs as well, as in like at what SNRs, because in order to make the system robust, the AI robust, you have to train the AI for different SNRs as well. For example, if you have not trained the AI for -30, wherein the signals quality will, or the signal waveform quality will not be that great, would not be that great, or would not be that high. In that case, the AI would not know. So there need to be certain feature extractions that need to be done to the AI to actually come up with a more robust solution on this. This is with respect to how AI is used on 5G networks. There are other ideas on how AI would be used for 5G. One of them being the scheduling of the users. So given that the 5G gets rolled out, we will get a lot of data from on the data usage pattern for a particular geographic area, on the mobility of the users, and based on that, the beamforming or the beam steering can be managed accordingly by the base station. So this is one of the aspect. The second aspect is on spectrum sensing. Mainly, for example, I give you a huge band mainly, and I give you a broadband mainly, and I tell you that, tell me what are the subbands, and tell me what are the subbands being used by individual technologies. Like for example, let's take a 1 gigahertz band, mainly any kind of 1 gigahertz band, and you need to know which part of that band is being used by 2G or GSM, which part is being used by 3G, which part is used by 4G, and which part will be used by 5G. So you can basically do a spectrum sensing and try to see the waveforms and have an AI in place which can tell you exactly what are the which subbands are being used by which technologies mainly, and which subbands are actually free as well. So you can actually have a collaborative spectrum sensing in between the users. This is kind of very important for increasing the data rate as well. So there are certain AI that has come into the communications domain. I'm very thrilled about the domain. That's why I felt like discussing with you, because this is very much in line with the 5G networks which will be coming in. The second set which will be coming in is basically on the radio, on the multi-rat system mainly. So with the multi-rat system, you will have the coexistence of several networks, right? So which network to be used when, for us to maintain a great data rate, is something which can be also scheduled and which can be also figured out using AI mainly. In order to work with this, the very important factor here is that we need to have a complete understanding on how the IQ architecture basically works. At the same time, it is also important that when we have the IQ architecture idea in place, how we are going to leverage on the IQ samples per se to actually give it when I say IQ samples, I have not basically dwelled much into it, but please take into consideration that the IQ samples are the baseband data. So what we are training the AI with are the baseband data mainly. So what finally is required, or the need of the hour, to have more and more data sets on baseband data, on how this baseband data data's features are different from each other, and how features can be extracted out to classify them. That's how actually the actual AI implementation will come into picture. Uh, I would like to show you another demo which I have made for a CISO based communication. It's kind of evolving toward. I'll show you how it evolves towards a MIMO setup mainly. Here, what we have done is there is a transmitter. What we intend to show is like a packetized structure, a packetized communication between the transmitter and the receiver. This is very important because many a times when we are working on theoretical concepts, or when we are writing papers, we need to actually test or validate certain things, right? So for example, you need to, or you come up with a particular way of particular packet structure, and you want to actually figure out whether that packet structure would be good enough for decreasing the bit error rate or not, or for would be good enough for maintaining the data rate or not. For all those reasons, or whether that frame structure would be good enough for frame synchronization, carrier frequency offset corrections or not. For all those reasons, first of all, what I believe that is required is to understand how at least a basic setup works, mainly an end-to-end setup works. So there is first a CISO system that I'm going to demonstrate, that I'm going to demonstrate an OFDM system, and then I'm going to show you a MIMO system as well. So this is a transmitter on the packet, and this is the packet which I'm sending right now. Let me stop the other VI, as I'm using. So now I would be transmitting this, right? And this is my TX constellation. This is my TX I diagram. So this is my TX constellation, and sorry, the system is a bit slow because I'm using the remote access. This is a transmitter, and this will be, I'll open up the receiver. So here, if I run this, you will be receiving the data here. So this is what we have done on the, so basically we are transmitting a stack of data, and we are receiving here using the USRP. So in here, what I wanted to show you is that all the concepts which are being used on the massive MIMO mainly can be theoretically can be demonstrated to the students in a very presentable way, wherein we are showing the match filter, the symbol timing recovery, the frame detection and synchronization, the channel estimation, and the channel equalization at the same time. So we will be transmitting some data, and we'll be receiving some data. Just to show you the backend of the code. This is how the backend looks like, wherein the baseband data that you receive, you do a match filtering on the baseband data. You do a RX symbol timing recovery, that is for aligning our signals, our symbols with the maximum energy detected. There is an RX downsample after that. There is a detect frame or a frame synchronization method, which on an OFDM we will be implementing it on the Smithel and Cox algorithm. Then there is a packet parser. I will show you a very interesting thing here mainly. So whenever you are receiving the data, right? Whenever you're receiving a data on a real communication link, your packets, when you're receiving packetized data, for example, uh, the the packetized data actually does not come as in like you don't receive the first packet first and then you receive the second and then you receive the third. It never happens. First of all, it's multipath fading is existing. So you might be receiving the sixth packet first or the fifth packet first, and the first packet might come later. So what has to happen is there need to be a packet parser in between that can actually take care and sort the packets together as well. So this is a very important concept when it actually comes to the physical implementation of things, of a real wireless link, wherein you have a transmitter is transmitting the packets one by one, but the receiver might start sampling the waveform at any point of time mainly, right? And that might be a point between your fifth packet and between your sixth packet mainly. So what you need to do here is that you need to actually have a sorting algorithm also in place that can actually bring the packets together and sort it out in a way that is intended for the user mainly, right? So there is a packet parser also involved. Then there is a channel coefficient. Then there is the generic channel coefficient, which is basically your channel estimation. Here I have used an LSM method, a least square method for that, wherein I use or leverage the training sequences on the frame. I use the training sequence created into a Toeplitz matrix, then take the pseudo inverse of that and figure out the channel parameters. Once the channel parameters or the channel coefficients are being found out, in that case I give it to the equalizer, and then a convolution happens between the equalizer coefficient and the channel and the received data, and you get the constellation back. So we need to run this. You see that the received constellation is something like this, a bit skewed out, and the equalized constellation is something like this, which is exactly what we want. And this is the RXI diagram. This is the equalized I diagram, which is exactly falling into place. So this is how a simple packetized communication between one transmitter and one receiver can be achieved. Now, the next is about finding out how to implement an OFDM system, wherein we will be including a multiple access layer as well, right? So the next demo that I'm going to show you is on an OFDM system. So this is an OFDM transmitter. We have taken around 5 users, user 1, user 2, user 3, user 4, user 5, wherein each user has certain data to send. Now I'm using an FFT size of around 128. That means the subcarriers that I'm using is 128. I'm using certain null tones in between. I'm having a cyclic prefix as well. So all the standards of the OFDM is being maintained, and we are putting the null tones at 0, 1, 2 and 3 position. The type of modulation that we are using, so it is basically a subset of what the CISO was. So the type of modulation that we are using is QPSK, and we are going to generate the user data, and the receiver would be able to cater to the user data. For the time being, since I don't have many SDRs in place, or I don't have all like 4 or 5 SDRs, so I'm using one SDR only and showing how individually each of the user data can be catered to mainly. So here what I will do is I will run the transmitter. I'll run the transmitter. I will run the receiver after that. And you see that the data gets well segregated out of it. This is the block diagram that we are building up here. There is this match filtering, downsampling, then we extract the training sequence, we put it on the channel estimator, then there is an endpoint FFT. We also see on the I'm talking about more on the receiver side because that's where the complexity of the processing lies. We are doing a serial to parallel conversion, doing an endpoint IFFT of it. We are removing the cyclic prefix, Then there is a FEC, which follows after that. That is your frequency equalization. That follows that. The frequency equalization is being used to equalize the OFDM symbols. Then we remove the null tones from there, and then from the parallel data we kind of put it back to the serial data. Now after that we do the symbol mapping, symbol to bit mapping. And since we already have the user preambles, we match it with the user preambles and segregate the data which is being found there. So an OFDM packet in general will consist of several user datas which are actually considered to be OFDM symbols. So an OFDM symbol will be a melange of several user symbols together, which we will be classifying based on the preamble and the signature being sent. So this is the OFDM implementation. I'm going a little faster since the time is running out. So this is the OFDM implementation with a convolution coding in place, where we are using a convolution coding for actually bringing in the FEC, the forward error correction in place. So the next in line would be to show you a MIMO setup. For that, I don't have the setup per se, but I will show you how the MIMO setup looks like. So in the MIMO part, what we have done is we are using STPC coding or Alamouti coding, where we are encoding with Alamouti, and then based on the maximum power being received on the receiver, we are choosing that stream, and that stream being chosen is basically used for demodulating it. So the transmitter and the receiver gets the part that I wanted to show you here is that we are synchronizing. Sorry. So the part that I wanted to show you is that there is a timing and synchronization which is involved when you are actually trying to implement the MIMO channel. I will just try to write it down and show it to you. So if there is two transmitters, TX1 and TX2, the setup is such that we have, as I told you on the massive MIMO part also, we have an octoclock, which is basically generating some reference signals and giving it to these guys. This reference signals, what it does is it synchronizes the LO and it synchronizes the ADC clock. The same goes for here as well as for here. So so suppose you are going for 2x2. In that case, basically you are having an LO synchronization signal from this timer and a ADC clock synchronization, which is called as the PPS signal from the timer. So there is a PPS signal and there is something called as a reference signal, reference 10 megahertz signal. Two that come. So this is currently the setup. The receiver side also is the same. It's the same on the receiver side as well, wherein the octoclock will give two signals to RX1 and two signals to RX2. And this is how the synchronization will happen between a transmitter and receiver. In terms of coding on a software-defined radio, the way to do it is that you start a trigger first. You configure a trigger first to start at a particular period of time. So you can see this. I told the receiver that you start the trigger after 4 whole seconds, and you can give a fractional second as well. We are not using that. Then what we do is we tell one of the USRPs to use we tell both the USRPs, since we are using the external octoclock. We tell both the USRPs to use the external reference, mainly the reference in and the PPS in from the octoclock. So both of them actually takes the reference from the same source, and hence the local oscillator as well as the ADCs are synchronized together. And then what we do is, in order to maintain the synchronization throughout the sampling, we say that at every next time age of the sample clock, or not of the sample clock, of the onboard clock, you basically use the same trigger. And hence we are able to synchronize the receivers like this, and with the same base code you can also synchronize the transmitters as well. Once it is synchronized and once you're receiving the data, then you can use a pre-coding method, you can use an ST, or you can use a space-time block coding method, you can use several MIMO coding methods to actually come up with a MIMO solution mainly. I would love to show you a massive MIMO setup, but like seriously, like I was unable to manage the hardware for doing the same. At last, I would like to take around 5 minutes more, and I would like to demonstrate to you IoT node setup, which you can see here. So you can see this. This is an IoT node, and there is I don't know whether you'll be able to see it from here or not, but there is a helical antenna which is connected here mainly. So the idea is that we can connect this node. There is a meter also. This is the meter. The blue portion that you see is a meter, which is also connected to the computer. So what we do is we send some query to an electricity meter, get the billing information or some kind of information from the meter, and we send it on a LoRaWAN network using an IoT module. And there is a Tata Communications network, Tata Communications IoT gateway, which is there somewhere in Bangalore, which will be picking up the signal and will be giving us the data on the server side. So assume that your institute, NIT Rourkela, has several electricity meters mainly, and we plug in this board to each of the meter. Then, and in certain time intervals, this board would be able to provide you with the meter information wirelessly. And this is what will happen during the densification of networks that 5G promises, wherein we will bring in wireless technology and submerge into a sensor network or submerge into a network of things mainly. So I would just like to demonstrate to you a very a demo on this. So suppose you want, so there are different meter parameters that you can go to. So right now, let's take, for example, the block load parameter. The block load parameter of a meter is like how much you have consumed the voltage or your current voltage, or what is your power factor at every half an hour mainly. So if suppose, for example, NIT Rourkela wanted to check wirelessly without going to each meters wirelessly, what is the block load parameter, or what are my parameters, power parameters at different instances, at different 30 minutes instances. So all you have to do is to plug in the board. There's a Python script that runs accordingly, and then you say update, press OK. This is the meter data that we fetch from the meter, and what we do is we basically fragment this into some packets, which this LoRaWAN device, keeps on transmitting. The chip that you see here is basically a LoRaWAN chip that is an RF module that transmits it at a high power, and then you would be able to see the data being received mainly. So with the IoT network coming into picture, this will soon submerge into the 5G network, and 5G will engulf all this IoT nodes together, and will try to provide the network requirement in entirety by itself mainly. So as you can see that the data packets which are being sent, this we are not sending, by the way, just to clarify, this we are not sending using the USRP per se, because the USRP does not have the capability to send across 10-kilometer range. So we are sending it using the module that I showed it to you, the small PCB based module that I showed it to you, and that we are using for sending it to a gateway which we are assuming would be somewhere in 10-kilometer radius from my office space. And then we are sending it is receiving it, reconstructing back the packet, and getting the meter data. So you see this, that we have 3 fragments that we have sent, and we have received this 3 fragments mainly. And then what will happen is on the downlink side, because we need to be sure that whatever data has been received data we have sent or transmitted has been received by the receiver. We need to have a feedback mechanism in place that tells us that yes, we have received all the packets, and that's why we send something called as a bitmap, wherein it tells us that all the packets which has been sent are correct because this is number one. And if there would have been an error in either of the packets mainly, in that case, instead of 0, a 1 will come and the position will be basically set as 1 in the, and the bit will be set as 1 in the position where there will be an error mainly, right? So there is a compression technique that we are using here, which is called as a static context header compression technique, where we are compressing an IPv6 header. The IPv6 header is a very is a very big header, mainly a 40 bytes header, too much of redundant information to send across a network. So we are compressing it using an algorithm called an SCHC, which is defined by the Internet Engineering Task Force. So we are using that, and then we are using the fragmentation technology provided by the IoT LoRaWAN network to actually send it across to, from the transmitter to send it across to the receiver. So these are the kind of demos that I wanted to show mainly. This is, I wanted to stop the session now and would like to take the questions, if any, because there are 10 minutes more. So I would like to stop the session. My name is RF and wireless tech consultant. Particularly, I've been very closely associated with the academia, because when I started after coming back from Germany, I started my career as an academic trainer, where I used to go from places to places, from different. I've almost like visited almost like 60 plus colleges across India, giving trainings on academics, on academic software-defined radios, on developing 4G and 5G systems. So my genesis of my consultancy actually began from academics. So that's the reason why whenever I get an opportunity to kind of present something on the academia, I don't miss it. And I have also been to NIT Rourkela, who has been the organizing committee for this. So I really thank the organizing committee for giving me this opportunity to present some few of my works and a little bit of knowledge that I have from my short span of like eight years experience in the RF domain. There is a lot more that is coming up on the 5G, and there is a lot more to explore, being on the practical scenario, because the challenge for me is whatever I learn, whatever I do on the theory part of things, I have to prove to my customers that this is on a practical scenario. So I have to kind of burn my hands with the different concepts and the algorithms that I learn on the 4G side, on the 5G side, or on the wireless tech side. The challenge for me, or the most major challenge for me, is to actually translate everything that I learn in my theory to actually bring it into a practical implementation. I had been already in touch with Annapurna ma'am, so thank you ma'am for allowing me this opportunity to, and also Shushmita ma'am. I had been in touch with her a very long back ago, so thank you very much ma'am for the opportunity, and I'm very open to questions. Please I will open the session for any questions and answer if there is. Hello.
Hello, thank you, Nilutpal, for your excellent presentation. Any questions from the participant side?
Hello.
Yes, continue.
Can we implement protocol stack with this MI instruments?
Sir, I didn't get you, sir.
Can we develop the prototype or code on this national instruments? LT protocol stacks.
Yes, sir. That there is already an LT framework, application framework, which is already there in the as a solution from NI mainly. So I would just show you mainly. There is already an LT MIMO framework which is there. So this is a MIMO framework, sir, application LT MIMO framework, which is already existing mainly. So there is already a setup that NI provides that gives you this mainly, sir. So this setup that you see is can be, so to answer your question, yes, it can be done. Yeah,
Okay.
to answer the question, it can be done using the NISDRs mainly with an application framework.
So is it coding in C, C++, MATLAB, like which language?
So there are two ways of going about it. Mainly, if you want to, if you're well versed with GNU Radio or C++ programming, in that case you can use this something called as ETAS Research USRPs. Okay, the ETAS Research USRPs work on open source GNU Radio, wherein you can use the open air interface for implementing the 4G LTE stack. Right. So there are two ways about it. So if you use NISDR, then you need to code it in lab. Okay. It is research USRPs, which actually uses open source GNU Radio. Then you need to code in C++.
Is it any relation with this? What is this? Keysight technologies. Keysight also same thing like this implementation is there. So I have gone through both the things. So what is any difference with the Keysight and this one?
You mean to say VSATs, very small aperture terminals?
In Keysight also some system view is there like lab view.
Right.
Yeah, is it any different with that this one and any like there is another vendor is like, but it's both together we need to work or what is a different?
No, sir. Like this is completely independent mainly. If you, the good part about working with the LabVIEW part of things is that it will be all under one umbrella. So you don't need to switch between different platforms. So to say, it will be one particular environment that will work on, that is LabVIEW mainly.
Okay. So now see for example layer 3 RRC protocol is there, MAC layer is there, so the upper layers or NAS layer also there. So how these layers we can implement in LabVIEW? So layer 1 is okay.
You cannot implement a network layer in LabVIEW because LabVIEW is mostly for physical layer prototyping. So here what National Instruments do is it provides you with an NS3 simulator integration. So you will be running an NS3 simulator and there will be certain APIs which will be given to you. These APIs will link your NS3 simulator, which will be your network simulator, with LabVIEW. Your physical layer stack would be running in LabVIEW and your network stack would be running in NS3. And
so do you mean to say like application higher layers will run?
Yes, sir. The higher layers would run on the NS3 mainly, wherein the data or the package that you make on the network layer, you can bring it to the physical layer using the network to using the NS3 plus LabVIEW APIs. So there is an API that connects the NS3 with LabVIEW.
Any is there ready-made? Just can you show me the protocol?
So right now I don't have it installed mainly because that's why I told you mainly like I had that thing, but I change that hardware because of this, because the offices are not.
Just remind of like how we integrate this layer 1 to upper layers and verify the software.
Yes. I will do one thing, sir. I anyway will be sending one mail from my side wherein I will be talking about the resources and everything that you can use. Perhaps I can make a note. I can send it across mainly. That would be better.
Yeah, it's better. I think like so for example one call or one voice call, one video call, how it is happening to transmitter and receiver.
Right. This is a project, sir, I'm already working on, but I'm not working on the LabVIEW side of things. I'm working on the GNU radio mainly, wherein I'm using the open air interface. So the open air interface comes up with what you said. It comes up with a solution like this. I will share you that link in some time, sir. With the map.
Okay. Actually, I am working in layer 3, layer 2, but layer 1 want to.
Okay, you are working on the L2 and the L3, is it, sir?
Yes.
Okay.
Right. Just I want to explore the things. Can you share the things if any possible?
Yeah, I'll definitely.
Yeah, Melody, you can share.
Right.
Thank you, Nilutpal.
Thank you.
Very good afternoon.
Very good afternoon, ma'am.
I think question answer session is over. Now?
Right. Right.
Okay, thank you so much for giving us time and explaining the 5G prototyping massive MIMO and millimeter wave system. Okay, in the using the lab view and all that USRP.
Right.
So, hope you are safe in this
Right,
period.
ma'am. Right, right.
Okay.
I'm right now in my hometown actually, Guwahati, but I had been in
Huh.
Bangalore for quite some time. Just came back actually to hometown.
Okay. Okay. So nice to meet you now.
Thank you, ma'am. Been a long time
Okay.
actually.
After a long
Pleasure.
time.
Yeah,
Yes.
yeah, ma'am.
So hope we'll also come to you will come to our institute again for a demo
Sure,
in near
sure, ma'am.
future. Yeah.
Sure.
Thank you so much. Thank you.
Thank you, ma'am. Thanks a lot.
Thank
Thank
you
you,
for
everyone.
yes. So next session will start